Hello. Thank you for coming. There's at least 10 or 20 of you here, so I can only assume that some of you got lost. This isn't a talk about agile or serverless, so if you think it is, you can now leave. I won't be offended. Okay, good. You all stayed. That's nice. So what I am going to talk about is C++ and some simple ideas to make C++ a little bit more observable when we run it in production. Just how we can add some instrumentation to it so we can get some data out of our code when it goes wrong. And I think this is necessary because in the C++ community we're doing a pretty bad job about talking about observability and monitoring. If you look at any other language community, they're taking this sort of stuff really seriously, and I think we're sort of stuck with syslog and printf as our abstractions for monitoring, and I think we need to do a bit better. So there's not going to be anything in this talk that's necessarily groundbreaking. It's going to be sort of basic stuff that you might come across, but it's about adding a bit more structure to what we're doing and sort of thinking a bit more about why we're doing it and not blindly just going into the sort of 3 pillars that everyone's talking about, but actually thinking, where do these overlap and how do we get the best data and how do we do this in C++? My experience with C++ started off, let's say, naively. I, for some reason, quite enjoyed doing it. But I didn't find out for quite a long time that running it in production is hard. I think you'd all agree. It's a bit like a science fiction-esque kind of wasteland where nothing is really there to help you, and there's a good chance you're going to get hurt along the way. So my first attempt at C++, many years ago, I knew 2 things about it. I knew that I would be programming C++, and I knew they were going to pay me to do it. That was basically all I had to know. I had no idea what I was really letting myself in for. As it turned out, what I was making was these network processing chips. And how you make these chips looks a little bit the same as how you make software. You write this code, and it tells you, and you tell, in the code you describe what the logic of the chip is. And through a very expensive and laborious process, you make a ASIC, which would end up in your laptop or servers or basically anywhere nowadays. But this process is extremely expensive. I mean, the conservative estimate from the company I worked at 10 years ago was between $5 and $10 million. I have no idea if that's still true with the newer process nodes or more advanced techniques, but it's really expensive. So you want to get this right first time. You really want to have as many attempts at making these as possible. So what they do when they make these chips is we test them very thoroughly. And this, as it turned out, was my job. I was writing C++ to test the design for these chips before they manufactured them and threw away a lot of money in the process. The problem with these chips is when something goes wrong, they're very hard to debug. You don't have a debugger. You can get some state out of it, but not a lot. You can't just throw on a debug build. I mean, it takes you $10 million to make the chip. You're not going to just make a debug version of the chip. And you can't just add some extra logging to find out what's going wrong either. So what we do is we add statistics to the chip. Lots and lots of statistics on everything. Number of bytes we receive, number of packets we receive, as much as we can fit in the chip. We really want to get as much information out of the chip after we've made it, because there are certain things that you don't know. Just like as with software, when it's running in production, things will go wrong that you didn't expect, or you might not be able to reproduce in a test environment. So let's contrast this to writing C++, actually writing C++ software, not using it for testing. Our process of putting it into production is a bit different. We have to compile it, package it, deploy it. But do we often think about how much this costs? You know, does it cost $1 million? $1,000? $1? You know, it depends, obviously, on so much the domain that you're working in. But there's a lot of reasons why it might actually be very expensive to deploy and change software. There might be restrictions on what software you can use in your production environment. For example, you might not be allowed to just install some tool off of pip or some tool off of apt-get. You might have to go through some laborious validation process before being able to install something. You know, and good luck if you're allowed to install a debugger. You might be working in an environment where there's very sensitive data involved. You know, if you're working on a database product and your database and your customer is storing healthcare data, it's very unlikely you're even going to be allowed access to the server to work out what's going wrong. You need to be able to take some data out from your environment and work out from there what went wrong. Embedded devices, always tricky, but improving a little bit. The firmware update for these things is usually slow and it's very risky because if the firmware update fails halfway through, then your device is now bricked. So we have to build in a lot of processes to make sure this is as robust as possible, but it is still risky, and we don't want to be updating these devices all the time, which is maybe why we end up with insecure routers in all of our homes, but you know, that's the fact of it. And now we're actually choosing to prevent changes to our environments. This concept of immutable infrastructure. And there's lots of advantages to doing this. Repeatability of deployments and such. But we're actually restricting ourselves in how we can debug it when it's in production if we can't then log onto a server and extract some data or run some tests in it. So when I think about my checklist for production ready, if it compiles, is it production ready? If it's tested, is it production ready? Well, production ready doesn't mean bug-free. You can absolutely say that for a fact. So you are going to need to diagnose bugs when they happen in production. And so I think if we're writing a checklist for production ready, we need to include that it is observable. And that's what we're going to focus on with this instrumentation. What we're doing is we're trying to make the code observable. So, what's instrumentation? Wikipedia says it's a collective term for measuring instruments, used for indicating, measuring, recording physical quantities. In the context of computer programming, instrumentation refers to an ability to monitor or measure the level of a product's performance. Good. That's a good definition. I mean, you can't go wrong with Wikipedia, right? I prefer to use the definition from Urban Dictionary, however. What Urban Dictionary says is, has this little example at the bottom, and they say, hey, John, look at that expensive instrumentation. But what Urban Dictionary is actually referring to is, if we're writing a C++ program, we're very worried about the overheads that we're incurring by instrumenting our source code. Because every time we add some logging or some counting to our code, we're slowing it down. And something we really care about if we're writing C++ might be performance. So, trust Urban Dictionary was the best place for C++ advice. Instrumentation allows us to observe deployed software. It can check that it's working as we want it to. It allows us to diagnose what went wrong and how it went wrong. And more importantly, ideally, the information we get lets us restore our system back to a working state as fast as possible. So that's one of our goals for this data. So remember, we're thinking about, let's be more structured about what we're doing. Let's just not splash logging everywhere all over our code. Let's think about why are we adding this instrumentation. Well, this particular piece of instrumentation is so I can diagnose connection failures to a database or file server, let's say. And this is in contrast to another goal of observability, which is measuring. So we're measuring performance of our software in production. Because quite often, bugs aren't functional bugs, but it's because something's running too slowly. And so in this case, what we're looking to do is improve the performance of our code over time. We're not looking for the root cause, but we want to observe a trend over time and see if we can improve our code, make it faster. Instrumentation is added to the source code. What this means is it becomes part of your product. It's not enabled. You don't turn it on and off. Well, maybe you can turn some more detail on at runtime, but it's always in your code. It's not compiled out with ndebug, for example. It's always there. It's in your production releases, and it's ready for you when you need it to debug a problem. And there are alternatives to this. You could experiment with the compiler adding instrumentation for you. Clang has quite a large amount of, they call them sanitizers. But what they're doing is they're adding instrumentation to your code for you to debug memory leaks or race conditions. And that's instrumentation, that's valuable. Just the same as debugs are valuable. But we want to focus on what can we add to our code so it's always there and ready for us without having extra tooling. So, printf. Who's used printf? Yay! So this is what we think of as logging, right? And to be quite honest, I find myself using debuggers less and less. I used to use it quite frequently, but I've got so used to not being reliant on them now, and actually relying on logging or printf or any of the other techniques to debug issues. And we joke about it, right? You know, printf debugging, it's kind of a meme, I guess, but I think it's valuable, and I think it is actually a really good way to think about debugging. So logging. How it begins. You'll get some message at some awful time of the night saying your software has crashed. And you'll ask, why is it crashed? What's in the log file? And they'll tell you, oh, stood bad alloc. Great. What do I do now? Well, at some point you'll ask them probably to reboot the server, and then that might fix the problem. With logging, what we're trying to do is we're trying to add a bit more information to what's happening in our code. Let's say, for example, we have this function that processes some data, process file. But when this function fails with some error message, you get some exception printed out, permission denied, that's going to be a really useless piece of information if it's included with a lot of other information. Or if the user just sees permission denied, well, permission denied from what? So we do this, and we might intercept the error and add some extra information to the error at the site of the error, because that's where we know most about what caused the error, is where the error originated. So you might end up doing this, add some printout, so we can at least see, there was a file, we were accessing a file when this error occurred, and we can find out what file. And you can quite quickly, from this, realize that maybe your file permissions were set up wrong on your file server or something like that. You have a route to then go and debug. What we might do in addition to that is add some context to the entire operation that failed. So we definitely want information about the error, but we also want information about the context that caused that operation that caused the error. So in this case, maybe a connection from a particular user from a particular IP address. That would be very useful to know, because then when that user starts complaining about why their connections are failing, we can actually find out why. From here, we can then sanitize this client error, because this permission denied is just going to confuse customers, confuse clients. They're not going to like it very much. So we can hide this away, and we can give a nice error. Let's say the request failed during I/O. So something went wrong when we were reading the file. The user doesn't want to know more than that, and if we tell them any more than that, they might just get confused. But what we do is we then keep all of the extra data in a log file on the server, so when the error occurs, we can find out and obtain the more detailed information that will help us, but we don't confuse the user too much. And if you get to a point where this becomes very structured, then you might start tagging errors with particular codes. If you ever get an error from some Microsoft product, then there'll be some code attached to the error, and you can then look that code up in a database to find out the issue, or perhaps how to fix it. And from here, you start thinking, oh, this is really useful. Let's build a library for it, because of course you should. So you see a lot of logging libraries that sort of implement this logging and severity model sort of based off this syslog standard that's existed for such a long time. So we might be able to log our errors with some extra information and slightly differently from the info. And maybe it does sort of the string formatting for us. And this is the status quo of logging. I don't think it's really moved a whole lot, particularly in, I think, C and C++ for quite a long time. Format string, severity levels, log rotation. Maybe you integrate them with syslog, and you can send them remotely and collect everything in one central place. Nice little features like that. But I think the whole thing is fundamentally flawed once you start scaling your system. Because if you ever get to a situation where you have a growing amount of log files, which you will do if your system or software is successful, then it's gradually going to become harder and harder to read these log files and work out why something went wrong. I mean, we're human, after all. We can't read this much data. I think I made it small enough so you can't actually read the text, sort of to prove a point. So the way we have been trying to resolve this is with magic. We process all of this data, put it into some really fancy database, put it through all these text parsers. Maybe we're using machine learning on it now because, you should be. But in seriousness, what this magic is, it is a huge ecosystem of software and services that let you search through the data and index it in a structured way. So you can do things like find errors that occurred on a particular host or on a particular component of your application. It can produce metrics and trends for you, so at what time of the day are the most errors occurring, for example. And again, produce alerts, so when something goes wrong, you get an email or a Slack message or a pager or a smoke signal or something like that. I still think there's a big room for improvement here, and this is, I think, becoming more popular as a concept, this idea of structured logging, and it's really not that hard to get your head around. Once you look at it, it's sort of common sense. Look at our log message that we had from earlier. User Steve IP something started a operational connection, and we had some log library produce this for us, and it munged all of that information into a string for us and wrote it to a file or sent it to a server. Well, what a lot of these systems do is they parse this data for us into a more structured form, because this structured data is much more easy to index and search, so we can have queries like find all the errors for user Steve. And so we end up writing these things, these horrendous regex patterns. If you've ever used Logstash, you might be familiar with these things. And you have to write a new one for every line of logging you add to your application if you want to structure it and you want to analyze it in any way, which is horrendous. And what's more ridiculous is we already had the unstructured data at the start. We already had a variable called user and a variable called IP address. So why did we then convert it to a string of text and then run it through a regex parser on some cluster running this enormous processing system and then put it back into a structured format at the end? And this is the point of structured logging. And when you look at it like this, it just seems obvious. Like, why did we do this? Let's just take those fields that we had and just omit them. and cut that step out, cut that step out, and cut that step out. And this takes your log data to such a higher level of utility. You don't need very complex software or infrastructure to analyze this structured data. I mean, a Python script would do a pretty good job. You could put it into a database fairly trivially. Just makes the data so much more useful. So this is something I think we should start talking more about with C++, because I mean, there are new logging libraries that appear fairly frequently. I think they crop up on a yearly basis, but they're all of this same, let's format some text into some human readable form. I think we should start thinking about maybe we can do better than that. Talking about making logging better and more structured, we start having to talk about tracing a little bit. And these two things, they're kind of referred to as two of the three pillars. You're talking about logging, metrics, and tracing. I think tracing is a lot more related to logging than many of us realize. And in its rawest form, it's just a form of logging. You might log an operation with a start and an end. This operation started, now it's ended. And usually what you can use this data for is you can work out what caused an error, and you can work out how long did the thing take. There's usually the two answers that you're looking for. And a really good example of this, one of my favorite tools, strace. If you've ever not used this, you should go and use it. What it lets you do is it lets you run a binary, precompiled binary, and it will tell you what system calls your application is doing. So if your application at some point in its life cycle opens a file and writes to a file, then it will quite helpfully print out that you opened a file, and what file you opened, and what flags it opened with. If you then read some data from the file, it will tell you that as well. So it gives you this information, but it also gives you the return code of the system call. So you can actually see now which operations failed and which didn't. So maybe if the opening the file failed, then you'll actually be able to see why it failed. It'll tell you, oh, it failed because the file didn't exist, or permission denied. But also, it gives you these timestamps. So it will give you a timestamp of, in this case, it gives you a timestamp of when the operation started and the duration of the operation. But quite commonly, what you'll see is you'll get the start timestamp and the end timestamp. Yeah, it's the same thing. But then you can see, okay, was it particularly slow opening this file? Was it particularly slow reading the data from this file? Really useful information. But tracing evolves from logging. If we have some file operation like we had earlier, we open a file and we do some processing on it, we might add a log to that bit of code to say, okay, now we're reading this file. We might then, later on, decide that we want to know when we finished reading that file, so we can work out either how long it took, or we want to know the error that might have come out of the operation. Did it succeed or did it pass? Did we get an error processing some data in the file? Did the file not exist? So on. So we add some logging to when the operation ended. And now this starts to look an awful lot like tracing. And so we start inventing tools and libraries for this as well. We might have some trace utility. Lets you start a trace and add some metadata to the trace. Here's the user, here's the file name, such and such. And sometimes these things are called a span as well. And then you can say when the operation ended. And with C++, maybe we can have this done implicitly or explicitly. The destructor, when it leaves the scope, it could do it for us. Or we could do it ourselves. That's a minor detail I don't think you should worry about too much. And we can emit this data as logs if we want to. So if we have a logging infrastructure, all we're doing is providing a more structured way to produce the data. It's not fundamentally different. I don't think you need to invest in a tracing system to take advantage of this, because it is just a more structured version of logging. Operations have a begin and an end. So we can write it out in the same way if we want to. File read begin, file read end. Sure, that looks fine. Maybe if we already have some tools for processing structured logs, we can apply it to here and do some analysis on those. Quite commonly, what we do with this sort of data is we don't omit the two events, but instead we'll just omit one event when the operation ends. Because they always come in pairs, we can say the operation ended at this point and it started at this point, or it ended at this point and it took this duration. Just keeps the amount of volume in your log a bit lower, and it makes analyzing the data just a little bit easier. The only disadvantage to this merging is that if an operation starts and is taking a long time, or potentially has hung for some reason, then you don't ever get the information that the operation started. So you just have to think about that trade-off of, do you want to make the data easier to analyze and more compact, or do you want the ability to debug events which potentially haven't finished yet? Tracing becomes more useful when we start talking about relationships. And this is when you might have come across the term distributed tracing. We have a trace of an operation that's occurring as part of a bigger operation. So we have this caused by relationship. This trace is caused by some other operation. And in this case, what we do is fairly simple. We just tag the operations with some sort of unique identifier, so we can create this relationship between the data. And there's a few ways to do this. And one of the hot topics at the moment is taking these identifiers but then passing them between services, or microservices, as we tend to refer to them. So we can trace an operation that actually passes through multiple layers of a stack. And again, this has sort of evolved so that we can just use a library to do this. We might have an operation on a trace object that lets us create a subtrace. So create a trace within a trace, or a span within a span. You might have heard that terminology. But this is where it gets even more confusing or interesting. You can actually take this concept back to the start, to logging, and start logging to a trace. What does that actually mean? Well, all that means is you're writing a log entry with an identifier to an operation. So you're creating this relationship potentially between a log, such as an error or a warning, and the operation that caused that error. So this is kind of confusing, right? Because originally, tracing evolved from doing logging, and we wanted to structure it more. And then we got all the way to the end, and now we're doing logging using tracing frameworks. So there's a lot more overlap between these two things, to the point where I kind of think the distinction is meaningless. It's all about there's some event occurring in your system, and what are the relationships to other events in your system? Well, that caused by relationship is just one operation caused by another. But then the two log entries, the two events that construct a trace, is just, well, this one is the start of the event, this is the end, and it causes this in between. Oh, and then there's a log error, which was caused by the fact you had to run that operation. So it's all very tightly coupled together. And this sort of comes back to this idea that if you just think about what you're doing with logging and tracing, you start to see, if you start to understand the reasons why you're putting a log message in a particular place, why you're putting a debug log, or why you're putting an info log or an error log, then you start to realize you can make this data much more structured, much more useful, and easier to analyze. What this lets us do is reveal processing dependencies, which I sort of talked about. I jumped ahead a little bit. We can say that we have some operation, and we can use that to trace errors back to the original cause. But it also is quite important for when you have systems with a lot of concurrency in. If you have operations that overlap each other, you need robust ways of linking the operations together. If all of your operations don't occur in a strict time order, then you're going to need a way to realize that that operation was actually part of this one, because there are going to be overlapping operations. And the typical visualization for this is these little timelines. You've probably seen pictures of these. They're pretty useful. It's just another way of letting our brains process a large amount of data. Visualization is an incredibly valuable tool for any data. And trace data is no different. So we could write a timeline to see when these file read operations are occurring. And we can immediately see, just by looking at this, you don't have to spend long, is that the first one's slower than the second one, and that they occur within the same 2 minutes of each other, or whatever. If we then extend that with these relationships, we can see which file read operations are part of a macro operation. So this connection to our server actually does 2 separate file read operations. That's kind of interesting to know. Why is it reading the file twice? Does it need the data from 2 files? Maybe it does, maybe it doesn't. And if you split it out by some of the attributes that you've tagged the data with, so if you tag the data with, for example, which user initiated that connection, then you can split this data up. And you can say that this data, this operation, this connection, actually only read 1 file. So that's kind of interesting. So if the first user is complaining, why is his operation taking longer, his or her operation taking longer, then you can actually work out why. It's reading 2 files. Why is it doing that? Maybe you can start asking questions. The distributed tracing aspect of it is the idea that these identifiers allow you to cross either process boundaries or node boundaries. And so you can trace back, let's say you have a remote database server. You could infer that this database request was caused by this connection. And that database request was necessary because it was implementing some authentication server, for example. But tracing is not free. And so we have to think a little bit about if tracing was free, then we could just put it everywhere and trace everything. But it's not, because every time we have some operation, it has to be logged, at least written to a file. Maybe it has to be formatted into some text. Maybe we can optimize that. Maybe we can just have some binary format for our logs and our traces. And so we can make the overhead really small. But as the number of occurrences of that trace grow, the overhead is going to grow. You can't avoid that. And this is why we have to talk about things like sampling and aggregation. So instead of logging and recording every event, we record every 10th or every 100th. Or in some systems, you can start a request and add some metadata to that request so that it causes the tracing to occur. So you can instigate a request with tracing enabled, for example. Or we can do aggregation. Well, maybe we don't care about every individual event. Maybe we just want to know how many or how long the operation is taking on average. So we could take a 1-minute average of all the durations, for example. Maybe that's enough information. This nicely leads us on to the topic of metrics. This idea of aggregating events into numbers instead of text or some sort of structured format. So take a step back. Metrics are just interesting numbers. And we obtain them by polling them frequently or computing them over a time window. So a 1-minute average, for example. or total number of connections, things like that. And you can see a lot of really nice examples of this in HTOP, another excellent tool, good debugging tool. HTOP you can run on a server and it just tells you some useful metrics about the server. It gives you the CPU usage, just a number, memory usage, another number with a different unit, process count, how many processes are running on your server, very useful to know, and even the uptime. When did your server last reboot, or when was it last rebooted by some rogue IT admin? Again, just another number of seconds since reboot. It's very flexible. And the great thing about numbers is you can very easily draw histories and trends of numbers. This example here shows the memory usage of a server in gigabytes. And we can see at some time the memory usage started growing rapidly, and eventually we get our stood bad alloc. I wonder how this could have been avoided. Could it be something to do with the fact that memory was growing? Well, if you didn't have this graph, you'd have no idea why you got stood bad alloc. Now you have a graph. Life's good. So what happened at 10:15? In the ideal world, what we'd be able to do is we'd be able to set some threshold and say, if our memory usage goes above 80% of the server's memory, then tell us and give us a big red warning in big bold letters. And then some diligent person or some unlucky person who happened to be on call can go and fix it before the error happens. How we achieve this is just by collecting data but storing it over a time period. So we store the history of the data. And it's actually a lot easier to store a very large history of numbers than it is of text, because numbers compress very well, and you can aggregate them. Instead of storing every single value you ever collected, you could say, well, I don't need to know the memory usage every 100 milliseconds. When I'm looking at 2 weeks worth of memory usage, I really only care about what was the memory every 5 minutes. Because I'm more interested in the trend. So numbers are much easier to store in large volumes than text. And from this data, we can build analysis and look at trends. What we want to do is, because you can find lots of really good monitoring systems that do this for you, but at a server level. So they'll monitor things like CPU usage and memory usage for you, and network usage, disk usage, things like this. All very useful data. But what we want to do is we want to add our own data to that. So from our C++ code, we want to inject our own metrics into this system so that we can collect a trend, for example, of the number of files we read, or the number of connections that occurred to our service. And we can look at the trends of those and use those to debug issues when they occur. A common format for representing metrics is this one here, open metrics. Simple text format. What's more interesting is the information than the format. So we give our metric a name, let's say temperature, if we have a temperature sensor on our servers. We can give it some tags. So, okay, we have this temperature metric, but which sensor is the temperature for? Which host name is the temperature for? The value, of course, say 24 degrees. And we might also explicitly put the timestamp in there. What we might also do is we might just record the timestamp that we poll the data from. And there's some trade-offs there about exactly how you do that, and it depends a lot on the frequency that you want to poll the data. But for this use case, let's assume we're polling it fairly coarsely, every second, for example. If you were polling data maybe every 10 milliseconds or 100 milliseconds, then capturing the timestamp of every one of those, there are better ways to do that. Counters again, libraries for these. Not a revolutionary concept, but you can find a few libraries that let you do this in a fairly easy way. I'm sort of going to express here my desire for a library and sort of the fundamentals of how you might build one if you wanted to, because it's really not complicated. It's quite common that you might have a counter class of some sort, and you can tag this with some metadata. And then when you want to record an occurrence of an event, you increment the counter. So we increment the number of files read. These counters are typically just wrappers around integers, and we make them atomic integers or some sort of thread-safe integer if we have lots of threads in our application and we want to be asynchronously polling the numbers from somewhere. But what's important is that that increment operation, that adding to a counter, is just incrementing an integer, maybe an atomic integer, if it has to be. We're keeping it as cheap as possible. When you record an occurrence that you've read a file, you're not sending an event to some remote server. You're not writing something to a log file. You're keeping it as cheap as possible. And this is really useful if you're writing performance-critical software, because you can actually put counters in places that you would think are fairly performance-sensitive. So don't restrict yourself. We collect these frequently using a method, some sort of poll method on the counter. Typically, we will have another thread somewhere in the application which will run through all the counters, collect the values, and then we will emit them somewhere. And so we get a record of every second or 2 seconds, for example. And it's okay that this operation is a bit more heavyweight. It's okay if we have to send this over a network or write this to a file, because we're doing it infrequently. If we've got 1 million events occurring a second, we don't have to do this heavy work 1 million times. All we're doing 1 million times is incrementing the counter. Only every second or every 5 seconds are we doing that heavyweight work of taking those numbers, formatting them, sending them, storing them. So it's extremely powerful. And if you're thinking, well, I bet that increment operation can be optimized even more than just incrementing an atomic integer, then you're right, and somebody actually wrote an entire paper on just making counting things really fast. So if you're really interested, then I recommend you read that. Hopefully you won't be as confused as I was. So where else can we put these counters? Well, I said we could actually put them in more places than you might expect. So what if not only do we count the number of times we read a file, but the number of times we read a line from a file, or a record from a file? You know, maybe this is a critical but fairly heavyweight loop. It's reading some data, it's processing it, it's parsing it. So it's not, you know, there's some work going on in there. Is adding this increment to it going to be a big overhead? It actually might not be. And if the data you're getting from that counter is valuable enough, then you might even take a tiny overhead. But you know, that's a trade-off you'll have to make. The data, when you start looking at this counter and you're actually running some code, start off at 0, and then when some operations come in, you start reading lines from the file, and the counter starts going up. Let's say, for example, we're polling it every second or 5 seconds. So this is useful. We can see that we are reading lines and the number's going up. But of course, we can do much better than this, and it's much more useful if we actually visualize this number. Now what we can see is that the number of lines we're reading goes up at some fairly linear rate, and then stops, and then goes up again. That might be because we're reading 2 files. We can see a lot of information from this graph. We can see how many lines we're reading from the file, because we read some lines, and it levels off, so we know we're finished. And we can see the rate that we're able to read lines from a file. And of course, you can graph that. And now what you've done, just by putting that simple counter in one of your interesting processing loops, you now get a really valuable performance metric. You can see the rate which your system's capable of reading lines from a file, but not averaged over the entire lifetime of your process, but potentially per request or per user. Because these two, from this graph here, is really hard to show, really hard to see that we're actually reading lines at a faster rate the second time round than the first time round. Maybe that's because we've got some disk cache helping us, so we're not reading everything from the disk. Then we have this sort of interesting lump in the data. In the first one, it drops off a little bit. And you would never have seen that if all you were doing was taking the entire duration of the operation and dividing it by the number of lines you read, because you would see the average for the whole operation. If you have this counter that's counting the individual operations, you can see how the rate changes. If you have concurrent operations in your system and you tag them with additional metadata, for example, which user is reading the file or which file you're reading, then perhaps you can actually see why that's happening. Of course, this is a contrived example, and with this data, you can then do some post-processing on it. And if you did want to have that average over a big duration, then you can do it. You've got the raw data, and these metrics databases, they're really good. They let you do all sorts of sort of aggregation functions on your data. So you could say, okay, well, give me the rate that I am capable of reading lines for the whole system, for every user. I don't care about individual users that much. And then maybe you're able to see an effect where, yeah, to start with, the performance is a bit slow, and then it gets better, maybe because of some caching, some effects like that. So really valuable. And all we did to get all of this data was just add a counter to one part of our processing loop. And of course, it wouldn't be complete if we didn't compare this and put this side by side with the other fancy graph that we drew earlier, that tracing data. If we know when the operations occur, then we can then correlate, for example, okay, this file read, these lines read, so we had that flat point in the graph. It's read some lines and it's read some more lines. We can see that that was two separate operations. And then we can use that to disambiguate it from perhaps some pause in processing, because that would then give us that sort of fall off in the rate as well. So by bringing all this information, this coarse information, this fine-grained information together, you can start getting a really good picture and build really good visualizations that you can use to not only debug performance issues, but functional issues as well. Because remember, if we're adding error information to these traces, then this would show up in this visualization as well. We might see that this file read operation failed, and we make it, I don't know, we put a big red sign there or something like that. It becomes very easy to trace back why at the top level the user saw an error and which error at the very low level caused that to happen. So I think we're finished. These sort of little code snippets that I've shown are something that I think is worth exploring a bit more, and I'm kind of trying to work on building something coherent out of this. But I don't think the libraries out there are sufficient enough for what we want to do to get the best quality data. We have lots of logging libraries, we have splattering of metrics libraries, but what I really want to do is to bring this together. And I think there's value in not treating these three pillars, logging, metrics. What's the other one? Tracing. Need some more coffee. Not treating these three things as separate, but actually seeing where they overlap and how the data can be used together. For example, that process file or process line event, maybe we sometimes want a detailed, more rich description of that as a log or a trace, but maybe sometimes we just want the count or the average duration. And if we had a system or a library where we could just annotate our code with this is an operation, this is a connection, this is something happening, then we can actually choose what we want. Okay, well now we want a very detailed output for this event, but for this event we just want a count or an average, something like this. So we can take as much detail as we can afford based on the trade-offs. So develop observable software. That's my number one point if you take anything away from this. It does require some effort. It's not free. You do have to think about where you put instrumentation into your code. But it does become incredibly valuable in production. If you've ever used a relational database, you will know that as a feature of every relational database, you can run a query and get an enormous amount of statistics about it. And they do that for a reason. It's so when users complain the database is slow, they have the tools to explain why it's slow. And instrumentation is a trade-off, especially if you're working on a system that has performance requirements. You have to be careful about where you put it, and you have to pick the right type of instrumentation for the event or the region of code that you're instrumenting. And the techniques are complementary. You don't just have to add source instrumentation. You don't just have to use externally added instrumentation or tools like strace. You can use both, and you should use both. Sure, use debugger if you've got it. Use strace if you've got it. Use everything at your disposal, but also prepare for when you don't have that luxury. So my closing thought is try and debug in development as you would in production. If you encounter a bug in the cozy confines of your development environment, then think about, okay, if this bug happened when I deployed my code on a server that I have limited access to and limited tooling available, what metrics, what logging would I need to debug that? And then when it does happen or something similar happens in production, not only are you going to know what information is available to you, but you're going to know how to analyze that information to work out what went wrong. And I think that's incredibly valuable. And for me, that's everything. If you have any questions or suggestions, then please email me, or sometimes I hang out on the CPP Lang Slack channel. I always put my email address up at talks, but I don't think I've ever got one email from anyone. I've even had people in the past tweet someone something about my talk, because I don't use Twitter or anything. So I sort of find out things about my talk indirectly through other people. I'm not very good at this whole social media business. But there you go. Feel free to email me, that's fine, or Slack is fine as well. So thank you very much.